तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the previous lecture, we have looked at the basic properties of transactions, namely the acid properties: atomicity, concurrency, isolation and durability. In today's lecture, we are going to see how these properties will be realized by the transaction processing system within the database manager. We will take a few simple examples, and through these examples we will illustrate how the transaction processing system will ensure the acid properties of the transaction. Here is a very simple example shown in the slides here. There are two transactions here which are shown, T1 and T2. T1 is a account transfer transaction, transfer of money from one account to the other account. Now 1000 rupees are being transferred from account A to account B by transaction T1. Transaction 2 is an interest payment transaction. So, it is actually crediting into each account a 5% interest into each of the accounts. Now, what is shown here is these T1 and T2 operating simultaneously on the banking system. Now, what we will do is we will try to understand these two transactions in terms of the various operations performed by these transactions. What I am going to do here is I will write T1 as performing several transactions or several operations. Now, the first operation that is performed by T1 is to actually take the account A and read the value of the balance that is there in this account. So, it is basically a read operation of the account. The second operation is essentially to add 1000 rupees into this account, and the third operation is going to be writing the value back. The same thing is going to be done for the account B. So, I will actually show that as the fourth operation, but the subsequent operations will not be shown here. They are self explanatory, one can understand after that the other operations. Now, this suffix here shows that this is the first operation and this gives the transaction ID. One is the transaction ID, and the one here indicates that it is the first operation. So, operation 1 indicates that this is the first instruction of transaction 1. This indicates that it is the second instruction of transaction 1, like that it is shown here. Now, if you basically take operation OIJ, it indicates that this is jth operation of ith transaction. This is the notation that we will be using. Okay. Now, as you can see here, this is basically a read operation on A. and this is basically a write operation on A. Okay. So, we have between the processing we have the reads and the writes happening on the data items. Now, we can also understand the transaction T2 also as shown in the slide as trying to do the following operations. O21 is going to be a read of A, and then the O22 operation is going to be an update on the value of the data item, and then O22, O23 is going to be a write of again A. The rest of the operations as shown in the earlier case for the B operation B. Okay. Now, what we are going to show you is what happens when these transactions are executed simultaneously on the database. Now, a list of actions form a set of transactions as seen by the DBMS. As you can see here, O11, O12, O13, O14 are set of operations constituting T1. Similarly, we have O21, O22, O23 constituting the set of instructions constituting transaction T2. Now, it is possible for these operations to get interleaved, in the sense that it is possible for these transactions, operations of the transactions to execute in an interleaved fashion. Now, when these get executed in an interleaved fashion, we basically call that as schedule. Okay. A schedule is nothing but a series of operations as executed by the database management system. Now, you can see here it is possible for these two transactions to execute concurrently. Now, a set of interleavings that were shown is the operation T1 constituting A equals to A plus 100 is executed here, then T2 is executed, which is equivalent to saying A equals to, this operation is executed here, followed by the T2 of B, then T1 again, B equals to B minus, this is one schedule which is called a possible schedule. We can call this as SC1 as one possible schedule. As you can see here, these two constitute transaction T1, these two operations constitute T2. Now, there is another possible schedule also shown in the slide there, in which case T1 and T2 are executed as shown here, but the other two operations are interchanged. This is executed before the other operation. Now, when we actually have these schedules, one of the important criterion for these schedules to be valid is to see that these schedules produce proper consistent results at the end of the execution. Now, this schedule 1 can be seen as shown in the slide as read and the writes on the various data items. T1 is basically is reading A and then writing A. It is reading the old value of the bank account balance of account A and writing the new value for the balance here. T2 is also doing a read of A and write of A, because you are computing the new value of A by calculating the interest that is payable for this account. Similar way, we can also write for write B and then read B and write B and read B and then again write B. Okay. What we are going to show you through this example is what happens when these reads and writes are interleaved from the consistency point of view. Now, you can see here the notion of what is correct from the execution point of view is shown here. Suddenly, we do not want transactions to execute one after the other, because then the throughput of the system will come down drastically. You want as many operations as possible should be executed in a concurrent fashion to actually increase the throughput of the system. Now, when concurrently executed transactions at the end of it, whether they can be translated into what is called a serial execution. Now, in this particular case, what you would like to say is T1 executed completely after T2, this is one possibility, or T2 executed after T1. As long as this is possible for you to say, we call this kind of a schedule as a serial schedule, and that is what is actually shown in the diagram here. A schedule which is equivalent to one of the serial schedules is equivalent to saying that either T1 executed before T2 or T2 executed before T1, that is one of this should be possible. Now, to see what really happens when the execution is not serial, that means when finally you are not able to deduct, saying that the execution of the transactions is not as per the serial schedule. I will take a very simple example and show how exactly we deduce the serial schedules. Let us take a case of a transaction T1 with operation X, okay, and then 1 2 which is actually a write of Y. Now, we can take another transaction T2 where basically it is a read of Y and then a write of X. Okay. Now, no matter how these operations are executed, as long as it is possible for you to say that all the operations at T1 have been executed before T2, which is equivalent to saying that if there is a schedule that says O11 X and O12 Y has actually finished before O21 Y and O2 X are executed by the database manager, this is equivalent to saying that T1 finished before T2. This is what actually we mean by a serial execution of the transactions, that is T1 finished execution before transaction T2 started executing. Now, it is also possible for you to also have the reverse order where all the operations of T2 have been executed before T1. This is a very simple and straightforward case where we can easily say when all the operations of T1 and T2 are executed in this particular fashion, it is very easy to see that T1 has actually finished all the operations before T2 started executing. The only case where you will have problems is when some operations of T1 have been executed in such a way that they are interleaved with the execution of the operations of T2, then the problem of deciding whether the schedule is equivalent to a serial schedule, that all the operations of one transaction finished before the other, becomes an important requirement, and that is what actually we are going to look at how that can be done. In this particular case, what we are going to say is all that will be required for us as a criterion when a schedule is produced is two operations are set to conflict. We say the notion of a conflicting operation is when one of them is a write operation. Okay. One of the operations is a write operation Now, to give you the little more simplistic view, let us say T 1 is trying to read a data item x and T 2 is actually trying to write the data item x. These two operations O 1 of some I, O 2 of some j are said to be conflicting because they are operating on the same data item and they are conflicting with each other, right. Here as you can see here, T 1 is reading the data item x, T 2 is writing the same data item x. Since both transactions are reading the same data item and one of the operations is a write operation, we say that these two operations are conflicting. Now, whenever we have conflicting operations like this, now first inference is here O 1 I and O 2 j are conflicting. Now, in transactions, if there is conflicting operations and there is a way these conflicting operations have been executed, let us say the conflicting operation in this particular case is executed in such a way that this is the order in a schedule. Now, this order actually determines that T 1 actually preceded T 2 because it is conflicting on data item x and T 1 has been executed before T 2. And now, this order should be preserved no matter what happens with respect to other operations. And as long as you preserve that order with respect to all other operations, we say that the operations have been executed in a serial fashion or the schedule is reducible to a serial schedule. This is the concept of serializability. Now, this is the important notion here is when transactions are executing concurrently, we need to ensure that the conflicting operations are serializable. All the conflicting operations are serializable. Now, here is a very simple case shown in the slide where it shows that where it is not possible to serialize, we need to actually abort the transaction. Now, in this particular case it is shown that T 1 actually is reading, as we go to the earlier case, T 1 is actually reading the data item A and then writing data item A. Now, if you look at the T 2, it is also reading data item A and then writing data item A. Now, the other part of the T 2 is read B and write B. Now, as you can see here, with respect to data item A, the order between T 1 and T 2 is T 1 is before T 2. Now, if you look at the data item B, it is coming in the reverse direction, which actually means that as you can see here on the data item B, as far as the conflicting data item A is concerned, T 1 is before T 2, as far as B is concerned it is T 2 before T 1. As you can see, this is on data item B and this is on data item A. Okay. Now, from this it is not possible for us to say whether T 1 actually has finished before T 2 or T 2 has finished before T 1. Since we can't now decipher which one is actually finishing before the other, this schedule is non-serializable schedule and this is what should be avoided. A non-serializable schedule shows that the execution of the operations will lead to inconsistency. The database will be in an inconsistent state when we have the operations executed in a non-serializable way. Now, in this particular case it is shown here that T 2 can commit, but T 1 has to abort. That is what was shown in the slide, saying that only B can transaction T 2 can commit, but T 1 has to abort because T 1 trying to commit here will produce a non-serializable schedule. This is also shown as, if you go back to the slide, you can see that this is shown as dirty reads, that is write and read conflicts. As you can see, B has been T1 has read A and B values, but it is writing the value at a much later stage, and now one of the later updates will be lost if you allow T1 and T2 to execute in this particular way. One of the operations will be lost, and that is the reason why this schedule is not allowed. Okay. We will look at other kinds of conflicts that can arise when transactions are executing. First kind of conflict that we saw is a write read conflict. We can also have a read write conflict and a write write conflict. What a read write conflict shows is, the example shown here is transaction T1 is reading the data item A, and if its value is more than 0, then it decrements. T2 is actually reading A and it is decrementing the value of A. Now, when T1 and T2 are operating concurrently, T1 is actually reading data item, whereas T2 is actually writing onto the data item. This is what we mean by a read write conflict on the data item A. With respect to data item A, both transaction T1 and T2 are conflicting in terms of T1 reading the data item and T2 modifying the data item, and this is what we mean by a read write conflict. Again, you can see that in this particular case, the value read by T1, if it is before the value is changed, will be inconsistent. Let us say right now the value of A is 0 and T1 reads it as 0, then it is unlikely to decrement that because it has read the value as 0. Now, if T2 also read the value at the same time as 0 and reads it as 0, then it decrements it as -1. So, that value is actually in conflict. The actual value that is read by T1 and T2 are not correct. Another example for conflict is the write write conflict, where two transactions, both of them access the data items and tries to modify the value of the data item. This is a case where it is shown here as two people simultaneously trying to credit into the same account, is shown as an example of a write write conflict. As can be seen here, T1 is actually writing the value of a value into the account, T2 is also writing a value into the account A as well as into B, and T1 at a later stage is trying to write the value into B. Now, as you can see in this particular case, the writes on the same data item will be conflicting, leading to non-serializable schedule. So, typically this is what we mean by a write write conflict. To summarize what we are actually seeing, I will give a simple example of an operation and show how exactly is the conflict serializability is to be achieved. If you take a transaction Ti and say Ti as an operation OIP and data item X, and you have a transaction Tj which has an operation Q on X. Now, we say that these operations are conflicting if one of them is a write. Now, when you say this is a write and this is a read, you have between OIP X and OJ Q, you basically have a read write conflict. The X data item is read by transaction Ti and it is being modified by Tj. So, this is basically a read write conflict. Now, if you say that this is a write write, typically what you see is between operation OI Px and OJQX, you see a write write conflict. Now, when there is a conflict between the two operations, whether it is a read write or a write write conflict, you need to actually serialize the operations by actually saying that they are executed in a serial order, which is what we mean by conflict serializability. Now, whenever there is a conflicting operations, you need to actually serialize the two operations, which is known as the conflict serializability. In this particular case, OIP x and OJQ x are the conflicting operations, and they need to be serialized in a particular fashion, and this is what we mean by conflict serializability. We are going to see in later lectures how the transactions are executed by the transaction manager to ensure that conflicting operations are serialized or serial schedules are produced by the transaction manager. One of the simple technique that is used is what we see as the two phase locking, and we are going to study that two phase locking as a technique for achieving conflict serializability later in our lectures. Now, here is actually what is shown as how exactly the transaction manager achieves some of these properties that we have been discussing. DBMS ensures that a transaction either completes and its results are permanently written. This is what we mean by committing a transaction, or no effect at all on the database. This is equivalent to saying that the transaction has been aborted. So, we have two states for the transaction, either a commit state or an abort state. In the case of a commit state, all the operations of the transaction are executed in full and they are committed. In the case of abort, no effect at all on the database as far as that transaction is concerned. Now, the idea of transaction manager is it controls the execution of the transactions. As we saw in this particular case, it controls the execution of the transactions in such a way that the operations of the transactions are serializable. Similarly, if you take the recovery manager is responsible for undoing the actions of transactions which do not commit. This is equivalent to saying that the recovery manager is responsible for ensuring the property of atomicity. All actions of the committed transactions survive any kind of hardware or software failures. This is actually known as writing the committed transactions onto a stable storage. What we are going to do is we are going to look at a little further into how the recovery manager ensures that properties of atomicity and durability. Now, what are the issues involved in ensuring atomicity and durability? The following errors can occur when a transaction is executing. First is it could relate to logical errors. For example, you are trying to withdraw some money from a bank account, it is possible that the account itself does not exist, or the account does not have sufficient funds. In all these cases, transaction cannot proceed any further. This is what we mean by logical errors. The transaction may have to abort because of logical errors. There could be system errors. For example, it is possible that there are problems of network, there are problems of system failures, temporary failure of power failure, in which case when the power comes back, you need to know what really happened for your transaction with respect to already started transactions. A simple example could be you go to a ATM and try to withdraw money from the ATM, and the power, when you actually press the button for withdrawing the money, the ATM stopped functioning, ATM failed due to various reasons. You would like to know whether the system has actually debited the amount from the bank from your balance or not. That is basically system errors. They could be system crashes, there could be a hard disk failure, the disk head could have been corrupted. So, there could be various reasons why the system did not perform, it could be a system crash. Now, all these errors are possible. when the system actually goes into any of these errors, you want to understand how exactly the atomicity and the durability properties can be maintained. A simple example trying to illustrate this point will be something like a file which all of us open on a Windows machine or any of our Unix machines. Now, here when you open a file as in an editor mode and tries to edit your file, there is no guarantee in terms of what happens when a power fails, because the file could be in a very corrupted state. There is no guarantees for you in terms of the state of the file, which all of us know. We keep repeatedly saving the file. When we are actually entering or writing some document, we try actually saving the document as many times as possible, so that when the power goes off or something else happens, we still save the portion of the work that we have actually done. We do not lose the file because of power failure, all the work that we have done. Now, the same thing cannot happen in the case of database systems, because here the more critical data that is being saved in the file. So, we need to ensure that whatever happens, when any of these failures happen, the system is still in a predictable state. That is the difference between ordinary file systems implemented by an operating system and a database implemented by commercial systems. They ensure that whenever these things happen, still the properties, the safe properties for the transactions, the ACID properties of the transactions are retained. To explain how these properties are retained by the system, we need to also understand the different storage types that are available in a computer system. A simple volatile storage, we basically look at a simple volatile storage, this does not survive system crashes. That means, when the system actually crashes, the storage is lost, the storage is volatile, it is lost the minute the system crashes. When you talk about non-volatile storage, the system actually survives these crashes. That means, the storage, whatever you write into the storage is not lost when the system crash occurs. A simple case is whatever is there in the main memory is lost when the power goes, whereas if you have written it onto your hard disk, it survives a power failure, because it is written into a more non-volatile storage. Now, we also have a concept of a stable storage, which is an abstraction of maintaining replicated copies in multiple non-volatile storage media, so that whenever higher disasters occur, we still have a way of getting our data back, and that is what we mean by the concept of a stable storage. Now, what we are going to see is how these concepts are used for actually achieving the atomicity and durability properties in the transaction manager. What we are going to show here in this particular case is what really happens when transactions have to roll back. The rolling of the transaction has to happen mainly because of logical errors or the system crashes, and hence it has to be restored back to a previous state. Transaction abort requires rollback, which means undoing all the actions of that particular transaction. Now, to ensure that rollback of a transaction occurs properly, what we have to do is all the writes of the transaction have to be properly recorded in what is called as a log file. The log file retains all the information relating to the writes of the transaction, and this will be used when the rollback has to occur. Now, if the system crashes, all active transactions during the crash need to be aborted when the system comes back. This is equivalent to saying that they will all be rolled back, and the information that is there in the system in the log file will be used to properly undo the transaction activities, whatever the transactions have been doing. What we are going to do is, again in this particular case, we will take a very simple example and see how exactly this happens. Now, here is the case where the logs are maintained and how these logs are helpful in ensuring the atomicity property, or how the atomicity property will be realized by the database manager. What is shown here is a simple case of writing the logs before the transaction starts executing and making sure that it is carried over whenever the data item is being written, or a new value for the data item is being written. What you can see here is the first log that will be written as far as the transaction T1 is concerned is what is called is the begin log, transaction begin log. Now, what we have is basically relating to a transaction. Every transaction is preceded by the begin transaction as a keyword. Now, this begin transaction actually tells the database manager to write what we see as a log. This is the transaction begin log. Okay. Now, this is the begin log has to be written onto the transaction. Now, in between the transaction does various operations, as we have seen there, it is possible that there are several operations which are done by the transaction in between, and then we have an end transaction. Now, this is actually the last instruction that is executed by this transaction. So, we will have a what is called a commit log, indicating that the transaction has actually committed, which is equivalent to saying that all these operations have been successfully executed. So, between begin and end, at any point of time when there is a crash, we need to actually recover back to the starting point, and this is what we mean by actually rollback. What we are calling as a rollback is basically rolling back all the things that the transaction has done to the beginning. This is what is meant as a rollback. Now, what we do is we actually ensure that whatever the transaction is doing is written onto this log, and this log will be used for rolling back the transaction whenever a crash occurs. For example, you can see that in the slide it is shown that Ti writes a data item. Now, as you can see, the first one transaction starts, there is a transaction log Ti start. Now, the second thing that you notice is Ti writes a data item. Now, there is a old value and a new value. Old value is the old value of the data item, and the new value is the new value of the data item x. So, there is a log that is written there which shows that Ti x old value and a new value is shown here. This is how actually the log is written. Whenever there is a change in the data item, we basically write the log, and now this log shows what was the old value and what is the new value. Now, when you come to the last transaction, basically you have a commit log, that is the Ti commit log. So, as shown here, we have a begin log and a commit log, and in between whatever is happening is being recorded there as shown in the slide there. Okay. Now, one of the things that we are going to look at now is how these logs can be used for recovery purposes, how exactly these logs can be used by the database manager to ensure that whenever those kind of failures that we are talking earlier occurs, how the system will recover back from those failures. Now, one of the things when writing these logs is, one of the things that one should remember is the IDs of the transactions are stored, so that we know to these logs pertain to which transaction. So, transaction IDs are appended with the log records to identify the transactions for which these logs have been produced. Logs are replicated and stored in a stable storage. This is also very important, because if the logs themselves are lost, then there is no way you can recover back. Logs, only assuming that the logs are written onto a stable storage, you can ensure that the transaction can be made to recover. But if the logs themselves are subjected to failure, then you will not be able to recover back, and hence logs are replicated. One of the assumptions that we make is logs are replicated and they are stored in a stable storage. So, when we say a log is written, we assume that the values relating to the log have been written on a stable storage, and it is possible for us to recover this information at any point of time. Now, as you can see here, we are also showing how these log entries will also be ordered, okay, ordering of the log entries. We say a transaction T can commit only if the log entry relating to that is saved on a stable storage. This is equivalent to saying, as you can see here, when you write this commit log is actually written onto a stable storage, then we say the transaction is committed. This is the point where it is possible for the transaction now to say that it is committed. Now, before this is actually written, this log is written, all the other entries before this pertaining to this transaction should have also been written onto the stable storage. You should never write the commit log before all the other log entries relating to this transaction have been saved on the stable storage. Now, only after writing the entries relating to the logs, you should write the data items themselves after this point onto the stable storage. This is very important. These steps are very important, because if you perform them in any other order, you will have problems in terms of recovering back. First requirement is all the log entries relating to this transaction should have written onto the stable storage in the first instance before you are writing the commit log. Only after writing the commit log, the data item values pertaining to the transaction can themselves be written onto the stable storage. The reason for this is simple. If you do not write the log values first onto the stable storage, there is no way, if something happens, to recover from that particular failure. For example, if you have written the data value onto the stable storage, now something happens, there is no way of finding out what is the state in which the transaction is, unless the logs are written properly. So, logs are the basis for the database manager to find out what is the state in which the transaction is when a failure has occurred, and hence it is important for you to first write all the logs relating to the transaction, then write the commit log, and then write all the data items onto the stable storage. This is how one needs to order or write the various things relating to the transaction. We will take a very simple example in this case to see how the two transactions can really execute writing their logs. In this particular case, it is shown T1 and T2. T1 is actually reading certain data items and writing certain data items. Similarly, T2 also is reading and writing certain data items. For completeness sake, we also have shown the initial values that are there in the database when these transactions T1 and T2 start executing. Okay. As can be seen in the slide, the initial values of A are A is 100, B is 300, C is 5, D is 60 and E is 80. Now, T1 when it starts executing, it is going to read the value of A, will increment it by 50, then read the value of B, increment it by 100, then write the value of B back into the system, then we will read the value of C. Now, C value is doubled, then the value of C is again written. At the end of it, A is recomputed as A plus B plus C, and the value of A is written. If you look at transaction T2, T2 is actually reading the value of A, it is incrementing it by 10, then it is actually reading the value of D, it is decrementing it by 10, then actually reading the value of E and reading the value of B, then E value is computed by adding E plus B and then writing a value of E, then D is recomputed as D plus E, then finally the value of E is written. What we wish to convey with this is the two transactions are simultaneously reading several data items and trying to modify. It is equivalent to saying that there is a set of operations which are going simultaneously in terms of reads and writes between these two transactions. Now, let us understand what really would have been the logs that would have been produced when this transaction T1 and T2 start executing. Now, when T1 starts executing, you can see that there is an initial log given there as T1 start. This actually shows that T1 started executing, that is a start log for the transaction T1. T1 is the ID of the transaction. Now, when actually T1 tried writing the value of A, the old value and the new value are actually stored in the database in the log. As you can see in this particular case, this log shows that A's old value is 100 and the new computed value is 150. Similarly, when B has actually been recomputed, we have a old value for B as 300 and the new value has 400. Similarly, for the value of C, it is 5 and 10. And finally, when the last computation for A actually took place, A is 150 and then old value of A is 150 and then the new value is 560. It is at this point of time that actually the T1 finished executing all its instructions and it is ready for commit, and that is the time the commit log is written, T1 commit log is produced at that point of time. A similar thing is shown for T2. As you can see, there is a start log for T2 and then we have various new values and old values for the data items that are done by T2 are also shown here, and finally commit log is shown for T2. Now, what really happens is once a failure has occurred, undo all transactions for which there is a start entry in the log, but there is no corresponding commit entry. This is equivalent to saying that, I will just go back to the previous slide to show what really we are saying. Now, you can say if for T1, when you actually a system crash has occurred, you can see there is a start log for T1, but a corresponding commit log is not present. Then all that you have to do is you have to actually undo whatever has been done by the transaction. For example, in this particular case, if T1 has actually modified the values of A, B, C, then those values have to be reset back to the old values from the new values. That is equivalent to actually saying that we have undone the transaction because it has not reached the commit state. Now, the other case is redo all transactions for which there are both start and commit entries, because these transactions have already gone to the finish stage. We are going to redo the transaction for all those for which commit start and the commit entries are there. And also if typically we have, if the data items are not yet written, this is what we mean by actually looking at whether the not just the log entries, but the data item entries are not still written, then we need to redo. But if the data item entries are also being stored on the stable storage, there would have been, along with the commit log, there would have been a complete log on the log book showing that the transaction has completed all the operations relating to it, in which case the redo need not be done. And this is typically achieved by what is called a checkpoint record. If the checkpoint record is entered into the log, whenever the system writes the data item values onto the database, the effect of the write operations are all committed on the transactions. Now, all transactions whose commit log entry appears before the checkpoint entry need not be redone in case of a system crash. So, the checkpoint is a place where you can decide whether when a commit log exists, whether you have to redo or need not redo those transactions. This is how exactly the database manager will ensure the transactions are executed atomically and they satisfy the property of durability. What we are going to see in the next class is how the concurrency control properties of the transactions are realized by the transaction manager. Okay.